Welcome back to Crystallography for everyone. In this video, we're going to see how A, B, and C are lattice translation vectors, and alpha, beta, and gamma can be used to form the seven crystal systems in 3 dimensions, and how the 7 crystal systems form the 14 Bravais lattices. The Bravais lattices are going to be extremely important throughout the series. Every crystal that we see in the real world, at least every crystal we're going to cover in this class, are going to belong to one of the 14 Bravais lattices. So it is very important that we get a solid understanding of them. I'm going to step through what parameters give rise to the different crystal systems. I do not think it's crucial to memorize these, but I do think it's important to know that they exist. The first one is known as the Triclinic System. Triclinic crystals are crystals where A, the magnitude of A, is not equal to the magnitude of B, and not equal to the magnitude of C. The angles, alpha, are also not equal. Nothing about triclinic is equal. In fact, very few crystals in real life actually have a triclinic structure. It is extremely rare. The next is known as monoclinic. In this case, A, I'll draw my A a little better. A is not equal to B. It's not equal to C once again. But in this case, alpha is equal to gamma, and they are both equal to 90 degrees. Neither of these angles are equal to beta. So again, there are very few monoclinic crystals. Our next system, number 3, is known as orthorhombic. Now we are getting to the crystals which are much more common. Nickel silicide, which is a crystal that we've seen in this course actually on the second slide of the first video, is an orthorhombic crystal. In this case, A is not equal to B, it's not equal to C, once again. But alpha is equal to gamma, is equal to beta, and they are all equal to 90 degrees. Alpha, beta, and gamma are equal to 90 degrees. So you can think of this somewhat like a rectangle from our 2D Bravais lattices. Our 4th crystal system will be Tetragonal. Where A is equal, it's not defined as, A is equal to B, not equal to C. Alpha is equal to beta, and gamma all equal to 90 degrees. Tetragonal is another very common crystal. So I will erase these to give myself some more room. Our fifth crystal system is cubic. Now this one is very common, very important, one worth memorizing. Alpha, or A, is equal to B equals equal to C. I think we all understand that from basic geometry. And alpha, sorry, is equal to beta, is equal to gamma. And they are all 90 degrees. Good old cubes. The sixth crystal system is hexagonal. Hexagonal crystals follow a different structure. They are somewhat dissimilar to all of the other crystal systems that we were looking at. So I'm going to create a video specifically for hexagonal crystals somewhere down the road. But for now, I'm going to leave them alone. And our final crystal system is known as rhombohedral. In this case, A is equal to B is equal to C. Alpha is equal to beta is equal to gamma. But none of these are 90-degree angles. So those are our 7 crystal systems in 3 dimensions. At this point, I think it's worth simply stating the 14 Bravais lattices. Here's an image I've taken directly from Wikipedia. What we have here are our 7 crystal systems, and then the 14 Bravais lattices. So the crystal systems provide the most basic lattice types. The Bravais lattices are somewhat specialized, I think is a good way to describe them. The leftmost column of the 14 Bravais lattices here is denoted with a P. Change colors. There's a P. That stands for primitive. These are the ones that we were just discussing. We also see the letter C here. That stands for centered. In fact, it stands for base-centered. So you can see there's a lattice point at the base of each one of these crystals. I stands for body-centered. And F is face-centered. I'm going to create more videos going into detail of base-centered, body-centered, and face-centered lattices. But I think we can point out some interesting ideas here. Monoclinic crystals have a base-centered Bravais lattice. They have a primitive Bravais lattice and a base-centered Bravais lattice. If we look down at cubic crystals, if we focus on cubic crystals, they do not have a base-centered lattice. They have primitive lattice, a body-centered, and a face-centered. I think you might be a bit puzzled as to why that is. And this comes into the concept of symmetry. We made certain definitions of the Bravais lattices of the Lat7 crystal systems. There is another area of crystallography that deals purely with symmetry. We can come up with all of these lattices using certain symmetry operations, things like mirrors and reflections. In the future, we're going to do this, but for now, I would like to just take it as granted. Cubic does not have a base-centered lattice, while it does have body-centered, face-centered, and primitive lattices. This might not be very satisfying right now, but in the future, I can definitely say we'll go into exactly why that is. At this point, I am sure you are tired of hearing about points, about lattice points. In the next video, we are going to discuss the concept of basis. We are going to finish simply discussing points, and we are going to start adding atoms to the points. Things are going to get exciting, I promise you. So I hope to see you in the next video.